Welcome to the second video in the PWM chapter of the Crystal Clear Electronics videos. In the first video, we put together a circuit that can adjust the brightness of an LED using pulse width modulation. We also got to know what a duty cycle is.
I would also like to welcome you all. Let's delve a little deeper into understanding how our connection works. For an easy understanding of PWM, let's first look at a simple example. Let's connect the so-called RC tag to the output, which is simply a resistor and a capacitor in series. This is also called an RC filter. Let's build in a 330 ohm resistor and a 10 microfarad capacitor. These are the components marked with R1 and C3 on the diagram. Here in the studio, we did it by keeping the flashing LED so that we could see what was happening at the same time. In parallel with this, we can also measure the voltage of the capacitor using the oscilloscope. If you view the voltage on the capacitor of the RC filter with an oscilloscope, you can see the capacitor charge and discharge, as we will show it here with Péter. Péter, can you please describe what we can see on the screen of the oscilloscope?
Yes. The blue marking shows the voltage on the LED and the red marking shows the voltage on the capacitor.
Perhaps you remember from physics lessons that the voltage of a capacitor is an exponential function of time. This is because the smaller the charge in the capacitor, the faster it charges. This is the steep rising initial stage. And when the capacitor is almost fully charged, it can only add charge more slowly, so the curve flattens out. Before we go any further, I suggest playing around with this circuit a bit more. To not only visually see what's happening, but also hear it, we'll connect this buzzer we found in the components list to our circuit and hear what's happening. We now hear an 11 Hz beep, and we see that our duty cycle is around 65%. What I'm going to do is change the duty cycle, and you'll hear that the beat stays the same, so the frequency doesn't change. But the duration of the beeps will be reduced. In parallel, we can also see that the capacitor has less and less time to charge. Now, at this 10% duty cycle, it can no longer charge to anywhere near its maximum voltage. Am I right?
Yes.
And we also hear that the beeps have become quite short. Now I'm going to go the other way with the duty cycle. We'll see that the capacitors will fill up nicely to full, but now they won't have time to discharge. And on the blue curve above, we can also follow the voltage of the LED. The LED has no capacitance, so it can follow the output voltage of the 555 IC. You can also hear the beep starting to become almost continuous, while the frequency remains around 11 Hz. I think we can eliminate this sound effect. Was this explanation clear?
Yes, absolutely.
Okay, I advise you to move on with the topic. Let's talk a bit about timing. If the capacitor C1 is replaced with a 100 nanofarad one, that is 100 times smaller than the other one, then the output signal frequency has to change from 11 Hz to 1.1 kHz. Let's see this difference on the screen of the oscilloscope. I will now replace this capacitor with a 100 times smaller one. And what should we see on the oscilloscope?
The frequency increased 100 times.
Yes, the value of the frequency is about 1.1 kHz. And what can we see on the voltage of the capacitor?
Well, we don't really see anything with that kind of time unit.
But the voltage difference between the maximum and minimum voltage is quite narrowed. That's because it doesn't have time to really discharge or charge, but fluctuates between an average value of voltage.
átlagos érték között hullámzik a feszültségérték. Tegyük azt meg, hogy
Now let's put an even smaller capacitor there. And with that,
piros jel, az RC
we'll see that the red signal on the capacitor of the RC tag is even smoother. We have 2200 Hz, so there's no time for them to recharge and discharge. We've got a very nice, smooth current. What we can demonstrate now is that by varying the duty cycle, we're actually going to vary this average voltage.
átlagos feszültséget fogjuk változtatni.
So I'm going to move the dial of the potentiometer in one direction. So now I'm going to increase the duty cycle, which has become 80% or 100%.
Vagy 100% lett, így viszem fölfel a feszültséget, hát pedig
Thus, I bring the voltage up. And if I decrease the duty cycle, the voltage of the capacitor on the RC tag will also decrease.
csökken.
Finally, it's time to bring out the multimeter and get some experience with it. I will take it out now. I switch it on in voltage measurement mode, paying attention to the measurement limits. I set this to 20 volts, so there shouldn't be a problem. And then I measure the capacitor's voltage.
És eközben kérlek a
Meanwhile, please adjust the potentiometer to see how the voltage changes.
és látom,
And I can see that as we change the potentiometer, the voltage magnitude changes here on my instrument.
Igen, de ugye
Yes, but in reality, we have a relatively flat signal on the capacitor.
próbáljuk, hogy
Let's see what happens when we measure the voltage on the series connected LED and resistor with a multimeter. Here, we know that the LED and the resistor are not capacitors, so the voltage really jumps between 0 and close to 12.
és az ellenállás együtt.
I will place it there then.
Nézzük, hogy viselkedik a multiméter egy ilyen esetben, amikor valójában
Let's see how a multimeter behaves in such a case when it is actually measuring a pulsating voltage.
pulzáló feszültséget mérünk vele. Látszik, hogy ahogy
You can see that as I change the duty cycle, the measured voltage changes.
feltekerem 100%,
So if I turn it up to 100%, we can see on the oscilloscope screen that we are measuring a voltage of almost 12 volts.
50%.
If I turn down the duty cycle, with the potentiometer to 50%, we should measure about 6 volts.
Körülbelül 6 voltot kéne érni, ez
It's now measuring 4.2 because I've gone down a little bit too much. And now I'm at 50% and we're measuring around 5 volts, right? And if I turn the pot all the way down, this will be explained later as to why the duty cycle can't be turned down to 0. I can only turn it down to 20%, and then the output voltage according to the multimeter is an averaged value, which is
1.9 volt.
very good. Thank you very much. To summarize what just happened with the multimeter, let's say, for example, that if our duty cycle is on 20%, so 20% of the time we have a supply voltage on the output of the 555 IC, then we can measure 20% of the supply voltage on the capacitor of the RC tag, or even on the whole RC tag and on the LED output.
a 20%-a mérhető.
At a supply voltage of 12 volts means that we should get 12 times 0.2, so theoretically 2.4 volts.
2,4 voltot kellene kapnunk. Tehát tudni kell a multiméterről,
You should know that the multimeter is averaging 2,
hogy simít. Különben
otherwise you would not be able to read the fast changing numerical values from the display.
talán foglaljuk össze.
We should summarize what we have learned from experimenting with the RC circuit.
This simple example illustrates that we can control analog systems with a high frequency digital signal.
analóg rendszereket. Itt a vezéreltség
Here, the signal we want to control is the UC3 voltage on the capacitor.
volt. És azért mondom, hogy
And the reason I say digital signal control is because, as you saw in the first video, the output of the 555 IC is a logic 0 and a logic 1.
között váltakozó jelet kaptunk. Kísérletezünk.
Let's keep experimenting, always thinking everything through to avoid problems.
Previous discussions have covered LEDs, and we will revisit this topic shortly. The LED ballast resistor serves as the resistor in this application. Its purpose is to establish the maximum current of the LED, which should be 10 mA for now. To achieve this, resistor R1 should be replaced with a 1 kΩ resistor.
Ismerős a kapcsolat.
This is a familiar connection. And let's explain how the 1 kΩ was calculated. From the 12 volt supply voltage, subtract the opening voltage of the LED of around 2.2 volts and divide this by 1 kilo ohm, then you get 9.8 milliamps, which is essentially 10 milliamps, which is perfect for us. The LED is in its correct place, and we should also mention that the LED is actually blinking. This circuit utilizes the inability of the human eye to perceive fast changes. The LED is turned on and off at speed, but our eyes will see a constant light source. But on the display of the oscilloscope, we can see that this is true. Therefore, we can control the brightness of an LED with the duty cycle of the signal. If you are curious about the blinking, replace the C1 capacitor to a higher value. We have seen this earlier, but we will show you one more time. If I place a higher value capacitor to the exact point, then we can see the blinking of the LED with our eyes.
I wonder what else we can drive with this PWM method.
It is much more spectacular to control a DC motor with our circuit. Fans used in computers are powered by 12 volt DC motors, which are appropriate for us. Of course, you can use any other DC motor, just make sure that the maximum allowable voltage of the motor is higher than the supply voltage. We may need more modifications depending on the current consumption of your motor. The maximum output current of the 555 IC is 200 mA, so fans with less current consumption can be connected directly to the IC output. It would not be able to drive a motor or fan which has a higher current consumption because it would overload the IC and it would break. Therefore, we need to connect our motor through a FET. This connection is shown in the figure. So now, I will attach the motor to the right place, the output provided by the MOSFET. I start to increase the PWM duty cycle, you can see that when I turn it down, the motor basically stops. And if I increase the duty cycle, I can increase the motor speed nicely. We can hear it humming, and this is where the FET takes place. The idea is that the relatively high current from the motor will not flow through the 555 IC, but through the FET itself.
I assume that we have one more interesting fact before we finish this video.
Yes, understanding the function of the D3 diode is important when dealing with components that have inductance, such as coils, electric motors, and relays. It is recommended to place a protective diode next to these components to prevent voltage spikes when switching or interrupting the current flow. Currently, the FET Q1 is used for interrupting the current, or, if connected directly to the output of the 555 IC, the IC's internal drive circuit is utilized. By interrupting the current, we are trying to suddenly eliminate the magnetic energy of the coil in the motor, which is not possible due to the laws of physics.
You are referring to the 13th chapter on DC engines, right? We heard about self-induction there. So now, self-induction voltage occurs at the motor's contacts from sudden switching?
Exactly. And this self-induction voltage can be of the order of kilovolt, so it would destroy the FET. On the other hand, if diode D3 is incorporated in the circuit, it will not allow the voltage at the MOSFET drain output to rise above the supply voltage, since the diode's cathode is connected to the supply voltage. This is because the diode will open as soon as its anode is at a higher potential than its cathode, so the current in the coil will continue to flow through it until the magnetic energy of the coil is consumed.
This was very interesting. Now we have to say farewell. You are all encouraged to join us for the third video, where we will delve a little deeper into timing calculations.
Thank you, Péter, for the encouraging words. See you in the next video.
This was the second video on the topic of PWM from the Crystal Clear Electronics curriculum. See you soon.